All right. So this week we're going to be talking about climate, the soil, and biomes. So starting with the climate and things that influence the climate, we have to talk about the sun, right? So all of that energy that Earth has originates at the sun. So it is coming from the sun and then interacting with Earth in different ways to change and transform, become different types of energy. About a third of that solar radiation that's coming in actually gets reflected off. So it's coming in at an angle, it hits the atmosphere, and just goes back out into space. The rest of it, 2/3, actually comes in. A lot of the ultraviolet radiation, like UVB, UVA, the stuff that we think is harmful, right? It'll damage our cells. A lot of that actually gets absorbed by the atmosphere, by the ozone, which is a molecule of oxygen. It's actually 3 oxygens together, which makes up an ozone molecule. And so a lot of that UV gets absorbed by these ozone molecules. As that heat comes in, as that radiation comes in, and it hits either the clouds to get absorbed or reflected, or it hits the ground to be absorbed or reflected, that energy can be released as infrared energy or as heat energy. So as that solar radiation comes in, it can be absorbed and then released as infrared. This infrared or this heat energy then dissipates. There are molecules in the atmosphere that are greenhouse molecules. They are molecules that actually reabsorb this heat energy and then re-emit it again. If you think about the atmosphere and all the different molecules we have in there, you're probably going to think of like oxygen, nitrogen, and water vapor. And if you take out the water vapor, like oxygen and nitrogen make up 99% of our air molecules, of the molecules in the atmosphere. Oxygen and nitrogen are not greenhouse gases. Water vapor can act like a greenhouse gas. Carbon dioxide acts like a greenhouse gas. Methane acts like a greenhouse gas. Nitrous oxide does. Ozone does. But the majority of the gas in the atmosphere is not greenhouse gas. But what they do, so those greenhouse gases take up that infrared and then they release it. And so it's kind of like taking that energy and then double heating the earth with it. Which is, I mean, kind of good. So if you think about what the average temperature on Earth is right now, it's roughly like 14 degrees Celsius. Without greenhouse gases, the average temperature would be negative 18 degrees Celsius. That's really cold. So, greenhouse gases aren't technically bad, but even small changes in the percentage of these greenhouse gases, I mean, again, if you think about all the gases, they make up like less than 1%. So even small changes can increase their influence on Earth's climate. And so over the past 136 years, if you want to take, I don't know, the 16 or 17 warmest years. So if you take the 17 warmest years, 16 of them happened between 2001 and 2016. That's in the past 136 years. So these increases in the greenhouse gases are obviously warming up a lot of places, but not every place. Antarctica has actually dropped their temperature 1 to 2 degrees Celsius in the past couple of years. So that's why we don't call it global warming. It's global climate change. So this is influencing the climate all over the world, not just by making it warmer, but by changing it, because Antarctica is getting colder. You're getting more severe storms. Areas that don't typically have certain types of storms are getting these storms, and there's a whole bunch of stuff that is changing because parts of the world are getting hotter or more hotter than they were. Okay, so greenhouse gases keep the Earth warm. But it's kind of an unequal heating of Earth, kind of like we said earlier, like Antarctica is getting colder while other places are getting warmer. We have an unequal heating of Earth because of the way that the sun strikes the Earth. So at the angle of entry, if the angle is steep, it's not going to give as much heat. So where one beam is coming in, it's actually spread over a wider area, which means that heat is less concentrated. Makes it feel cooler, right? If it's one beam at a very focused point, that's going to be a lot warmer, okay? Another thing is the amount of atmosphere it passes through. The more atmosphere it passes through, the more that can get absorbed and reflected, and so the less heat that makes it to that area. And then, of course, the reflectivity of the surface. So if you look at sea ice, it is very reflective. So not a lot of that heat gets stored here. It gets reflected off of the sea ice. Fresh snow also reflects off a lot. You might have noticed this if you look out on a snowy evening. You're like, wow, it's really bright outside. That brightness is the reflection of light, right, off the snow. If you go skiing, you probably need to wear like sunglasses or tinted goggles because of that reflection off the snow, and you might want to wear sunscreen because of the reflection off the snow. That reflection off of snow and ice, off stuff, is called the albedo. And so this is the fraction of the solar energy that gets reflected by an object. And snow and ice reflect a lot of solar energy, so they have a really high albedo. Water, somewhere between 10 and 60, so depending on the water, it can absorb a lot or reflect a lot. And then croplands are 10 to 25, and cities are like 5 to 10, so asphalt really absorbs a lot of that heat. And you may have noticed that if you like step outside on a road and you're like, wow, that road is just like emitting this heat, like the heat is just coming off of it. And so you kind of see these things where cities act like a heat source because the asphalt brings it in. They can be like up to 10 degrees warmer than the surrounding area because of all the heat that gets trapped in the city from the asphalt, because it is absorbing a lot more of the sun's energy. And so, depending on the surface, how much atmosphere, and the angle that it's striking, you're going to get differential heating at different areas. And the Earth, as we're going through space, it's tilting, right? Like in spring and summer, in spring it's kind of like this. And in summer, we're tilted, where the northern hemisphere is getting more direct sunlight. And then in winter, it is getting less direct sunlight. And so it's going to feel colder because we're getting less energy versus in the summer where we're tilted towards it and getting more energy. And so that's something where the sun is around the equator. It's not always on the equator, right? Because you have that tilt. So sometimes it's a little higher, sometimes a little lower. That's what you call the solar equator. And the fact that you have the sun warming different areas unequally gives rise to some pretty cool stuff, like wind. So warmer wind, warmer air is less dense. It spreads out, right? And so it rises. Just like water, as it gets warmer, it gets less dense. A lot of things, as it gets warmer, gets less dense. The molecules spread out. And so warm air rises. So if you're right here and the sun is focused on you, your warm air is going to come up, right? As it comes up, it starts to cool off. So why does it cool off? This is something called adiabatic cooling. As you decrease the pressure on something, it has less molecules to bounce into, and so it's hitting less air molecules less frequently, and that causes a loss in temperature. So as you go up and the pressure decreases, you cool off. And of course, the inverse is opposite too. As air comes down, it has more things to bounce off, the pressure increases, and it gets warmer. This is something you could try if you had a pump anywhere, where you can condense a lot of air in an area, and it will warm up. As you increase the pressure on things, they get hotter. That is adiabatic heating. If it's getting cooler because of less pressure, that's cooling. And so we have this ITCZ, this intertropical convergence zone, with these things called Hadley cells. And so this tropical convergence zone is going to be around that solar equator, where you have a lot of the sun's rays contacting the surface. And so it's going to be warming this air. As it warms the air, that air goes up, which creates low pressure. And so areas from high pressure are going to move to low pressure. And so the air moves from this high pressure area to this low pressure area. As it's moving, it is warming up and collecting moisture. As it comes up, it cools off. As it cools off, the amount of moisture it can hold decreases. So hot water is able to hold a lot more liquid. Cools off, that water condensates, collects, and then makes clouds, potentially rain. And then you'll have that rain, that air cools off, also becomes more dry, and then falls back down to where this air has moved out of the way. And this is something called a Hadley cell. Since that solar equator is moving around the Earth, you're going to have wet seasons and dry seasons around the equator, inside those tropical zones. They don't have winter and fall because the sun is still hitting there pretty solid, versus outside of the tropics, you're going to have, in the temperate areas, you're going to have seasons like winter and fall and summer and spring because of the tilt of the Earth. So these Hadley cells are creating wind, right? They are bringing that air and moving it around. Another thing that influences the flow of wind is the Coriolis effect. So Earth is round and it's spinning, but it's spinning at different speeds because it's smaller at the top, bigger in the middle. And so for everything to match up as it spins, it's actually spinning faster at the equator than it is at the poles. You could think of it as somebody who is standing in the middle and they have a long rope hooked to somebody else, and they're like, okay, do one turn. That person has to run all the way around where this person just turns in a little circle. So this person has to turn a lot faster to keep up with this person turning right here. And so you can see at the equator, we're spinning about 1,670 kilometers an hour, versus up here at the pole, you're only spinning 291 kilometers an hour. So that's a big difference. That's over 1,000 kilometers an hour difference in the velocity of the spin. And so while you have these Hadley cells bringing in wind, moving the air, you have the Coriolis effect that with the spin of the Earth is forcing these air down and towards the middle. So the Hadley cell is bringing the air in. The Coriolis effect is deflecting that path. So it's like if you take a baseball and you throw it, but you're on a platform that's spinning, it's going to look like when you throw that baseball, that platform spinning, and you have your target right here, and you throw the baseball straight for the target, it's going to miss because the platform is spinning, right? And so it's going to look like it curves, but that's just because the thing that you're throwing over is moving. And so that's the Coriolis effect, where you get this deflection due to the rotation of an object. And in this case, it's going to be the Earth. And so we're spinning faster here, slower here, and so you get westerlies and southeast winds, northeast winds. Okay, so that's how the sun heats the world unevenly. That uneven heating causes Hadley cells, sometimes polar cells too, and wind. Coriolis effect influences your perception of that wind and which direction that wind is blowing. And that really kind of covers like the surface, the air in the atmosphere, but the wind and the sun aren't the only things that influence climate. We also have our ocean currents. So ocean currents, kind of just like wind, like we have differential heating in the ocean. Lighter water is going to be warmer. Okay? So near the equator, you have less dense water. So much so that at the equator, the sea level is actually 8 centimeters higher than you would find at the poles. So it is actually higher because it's less dense, because it is warmer. That warmer water moves out of the way, right? And it moves away from the equator. So here you can see your equator. That warmer water will move away. Cooler water moves towards. Moving towards, moving away. And so you get these big currents, like your North Pacific current. You get your South current. You have your North Atlantic current. You have your Southern equatorial current. And you end up getting these different currents. This large-scale water movement between the continents are called gyri. And so this would be a gyri, looking at this current as it moves from Asia to North America, from Indo-Australia to South America, are these gyres. As that water is warming up here, it is going away from the coast, and as it pulls away from the coast, that allows cold water to come up. And it allows this cold water to come up to the surface. And these are called upwellings. And upwellings are really important for fisheries because these cold water that is coming from down here in the Arctic or Antarctic or from up here in the Arctic are nutrient rich. So they have a lot of nutrients in them. And so when they come up, that's a lot of food for fish to feed on. Allows them to reproduce, make more fish. So these upwellings are really important. So as that warm water moves away, it allows the cold water to come up and increase fish populations. But how important are these currents? How much do they influence the climate for the land masses? I mean, of course, like warm or cold water will influence the climate in the ocean, but does that influence the land at all? We kind of have a natural study for this called the El Nino Southern Oscillations. So every 3 to 7 years, the winds on the Pacific Ocean switch. And so they go from blowing east to west to east. And so these southeast trade winds can change direction and start blowing towards the west, which influences the surface water. Typically, it looks like this. So the warm water and the trade winds are moving away from South America. So that cold, deep water, so you can have those upwellings, right? So here you can see that Peru upwelling. When you have the El Nino event, though, means little boy, typically because this happens around Christmas time, you have the warm water going towards the coast. And so we're not getting this upwelling. In normal years, with the upwelling and the warm water going off this way, that warm water is going to evaporate and it's going to cause precipitation. That happens up here. And so you get a lot of normal wetter seasons around California in the upper east or west coast, so like Oregon, Washington. During El Nino years, that warm water moves this way, and so you get a lot of storms right in here. So they're not happening up here, they're happening down here, and so you get really wet Ecuador all the way up into Mexico during El Nino years. That causes really dry weather up here, and California is pretty notorious for fires. During El Nino years, even more notorious because it's a lot drier. And so this happens every 3 to 7 years. A couple years back, it was so bad that the fishing industry in Peru and Ecuador collapsed because they didn't get that upwelling and the water was so warm that there just wasn't any fish to fish from. They weren't reproducing, they weren't there, they weren't eating. And so it can cause really drastic, catastrophic, economical impacts for these areas. And of course, in one El Nino year, like, it caused it to be really warm over in Malaysia, and they had a really bad drought. Another year, it really influenced Africa and the amount of precipitation they got. And so, just from this one current switching, you can have drastic climatic changes. So, what would be something that could switch the currents in the world? Well, they kind of flow along basins in the bottom of the ocean. You have these deep currents and then some more shallow currents. A lot of these deep currents are done by this thermo-highline circulation. Thermo talking about the temperature, highline talking about the amount of salt. And so as water gets saltier, it gets heavier. As it gets colder, it gets heavier. And so that kind of brings this cold water down. Right? And so, when it cools off, comes back up and then gets pulled down again. As water freezes, like up here, so our warm water comes up, seawater freezes, the salt in the seawater doesn't freeze. And so the water closer to the poles are actually going to be a lot saltier because that salt is not freezing. That causes that water to be heavier. So does being colder. And then it flows down into our basins. And then can come up and warm up. That warm water pulls it away. And it's just this big conveyor belt. With the polar ice caps melting, that is releasing a lot of fresh water. That fresh water desalinifies the salt water, so it makes it not as salty. Also, with it being warmer, it is not as heavy, which means this conveyor belt is starting to slow down, which can influence the overall currents that we find in the world. And of course, this is where those upwellings come from, is from this cold water. So what happens if our thermohaline circulation stops? Well, then you're not going to have upwellings. You're not going to see all these differences that we see. The entire climate on the world can be influenced drastically if this breaks down. And so you want to keep the ice at the poles, because without it, you could break this down or change this, and things get to be really weird. So that's the ocean and the wind and the sun, and we'll pick up with smaller climatic things next time.